Hi, I'm Juliette Marie, presenting LUDVIG, a method for transferring 2D visual features into 3D Gaussian splatting scenes. This is a joint work with Romain Ménégo, Michael Herbel, Diane Lerlu, and Julien Méral. Our work builds upon Gaussian splatting, where a scene is represented by millions of Gaussians, each with a position, a size, a color, and an opacity. These Gaussians are rendered from any viewpoint using alpha blending, and all parameters are optimized through a projection loss that aligns the rendered image with ground truth view. To enable 3D semantic understanding, prior works have attached not only colors but also generic features from models like DynoV2 or Clip to each Gaussian. These features can be rendered with the same alpha blending equation and also learned through a reprojection loss. This approach works, but with high-dimensional features, it becomes extremely costly. Training can take hours, whereas rendering a trained scene back into 2D takes only a few milliseconds. So we searched for a simpler way to uplift features from 2D into a trained 3D scene, as simple as when rendering from 3D into 2D. And our proposal is the following. We define each Gaussian's features as a weighted sum of the 2D features of the pixels it affects during the rendering. The weights are the same alpha blending weights, renormalized to sum up to 1. And intuitively, these weights measure the correlation between a Gaussian and a pixel and can be used in either direction, from Gaussian to pixel or from pixel to Gaussian. Our equation can also be written in matrix form. With W the matrix of blending weights, rendering is simply W times the Gaussian features, and uplifting is W transpose times the image features followed by renormalization. Another way to see it is by comparing our approach to gradient-based optimization with the L2 reprojection loss. Then our uplifting corresponds to taking just one gradient step from 0 features, and D can be seen as a preconditioning. Let's now look at visualizations. In the middle, you see a PCA of DynoV2 features extracted independently from each image. These are coarse, patch-level representations, and on the right are the features obtained after aggregating all the 2D feature maps into 3D using our uplifting and reprojecting back into 2D. And we get sharp pixel-level representations. We also evaluated our approach quantitatively through segmentation. Given some scribbles on a view, the task is to provide 2D segmentation masks on all other views. And here are some results when applying our uplifting to SAM. In the middle, SAM predictions are made independently on RGB inputs, and to do so, scribbles are uplifted and reprojected to form point prompts. And on the right is the results of aggregating all predictions into 3D and reprojecting back into 2D. And we see a clear accuracy gain, especially on complex masks. We also evaluated the quality of our 3D DynoV2 features with the same task, but segmentation with DynoV2 is not straightforward. A naive approach is to compare features of each pixel to those in the scribbles. And on the right is the result. We isolate the central object, but also the two side objects that look similar in DynoV2's feature space. So to only isolate the central object, we need to leverage geometry. And we propose to do so through graph diffusion. Starting from scribbles uplifted into 3D, we build a graph where each Gaussian connects to its neighbors with a weight defined by matrix A. And the weights in A have two terms, a pairwise feature similarity and a regularization, here in red, that compares each Gaussian features to those of the Gaussians belonging to the scribbles. Defined this way, the diffusion process propagates the initial 3D signal from the scribbles within the objects, stopping at its borders thanks to the regularization. The logic used to segment based on scribbles also applies to textual prompts using Clip. Given a text prompt like a bag of cookies, we compute its similarity with 3D Clip features, but the result is noisy. And diffusion using DynoV2 features refines these activations into a clean 3D mask shown on the right. To conclude, LUDVIG is a learning-free way to uplift 2D features into 3D Gaussian splatting scenes. It produces rich 3D semantic features that enable segmentation from sparse scribbles or text prompts, but limitations remain. We still depend on the pre-trained Gaussian splatting reconstruction, which may degrade with blurry or low-quality inputs. Thanks for listening.